Hello, young scientist. My name is Ayush P. Gupta, and in this video, we'll be seeing what is a rigid body and what are the moment of inertia of the rigid bodies. Okay, so this is something about me. I'm a BTech IIT Roorkee graduate. So let's start with what is actually a rigid body. Okay, so in physics, rigid body, in especially in rotations and mechanics, this is very important term. Okay, so please try to understand this carefully. Okay, so the first point is rigid bodies is a body in which deformation is zero. Okay, that is if you take a rubber ball, you can compress it. Okay, or you can take even the rubber ball is very less elastic. Okay, so take this like your anything that is board etc. Even that also deforms when you apply the force. Okay, so in physics, the body which that's a theoretical body. Okay, no body is there in the world which doesn't deform on the application of the force. Okay, so in theoretically the rigid body is a body in which deformation is zero, or technically the distance between any two given points. Okay, that is the any two given points on the rigid body remains constant. Okay, that is you take the 2 points on a rigid body and you just apply the compression. Okay, you will see that only the distance remains the constant. Okay, that is the distance between them doesn't changes. Okay, regardless of any external force. Okay, so with this as we have seen in our last video that how to calculate the moment of inertia of a particle. Okay, which was I is equals to mr square. Okay, now because rigid body is actually a collection of multiple small particles. Okay, that is infinite small particles are arranged in some fashion which actually gives you rigid body. Okay, so to calculate the moment of inertia of the rigid body, you just have to take the individual particles moment of inertia about an axis. Okay, and just add up them. So it will be sigma of r1 square plus m1 square and so on. Okay, but you know that when your mass is very small, then you can convert that sigma into integral. Okay, so remember this thing that integration is actually the sum of very small uh, this elemental particle. Okay, that is the dm. Okay, so if you sum them and do this integration, you will get the moment of inertia of the full body. Okay, I hope that you know what is integration is actually. If you even don't know, just remember that a moment of inertia of a rigid body is given by integral of uh, r square into dm. Okay, so remember this thing that here because r varies with the mass. Okay, so that's why we cannot take the r outside. Okay, and if it's something like a ring type. Okay, so because then each mass will be at a constant distance capital R, so then we can take it out. Okay, so in this, because the mass is distributed non-uniformly over the this axis from the axis of rotation, that's why we take this formula. Okay, so this is also known as the elemental moment of inertia. Okay, that is the r square dm only. Okay, now let us see what are the example the various moment of inertia of the various common rigid bodies. Okay, so if you take the circular ring. Okay, as you can see, again I have said because here the mass is fully distributed at a fixed distance or the radius from the center of axis. Okay, that is if you see this, it is fixed, so that's why you can take this r becomes constant, so you can take this out. And if you do the integration of dm, okay, that is integral of dm, then you will simply get the mass of the ring. Okay, so that's why I is equals to mr square. Again note that this sense of rotation, that is anti-clockwise, doesn't really matter in the moment of inertia thing. Okay, moment of inertia is about an axis. Okay, not like it whether the body is rotating anti-clockwise or clockwise. Okay, for the solid cylinder, remember this thing that solid cylinder you will have mass at different distance from the center of rotation. Okay, or the axis of rotation to be better. So that's why you need to perform the integration, and you will get I is equals to half mr square. Okay, now for the hollow cylinder, again that's a ring type of case, that is you extend ring in something this fashion. Okay, that's why in the hollow cylinder case it is simply mr square. Okay, now we will be dealing with the proof of these in our later video. So for now you just remember these formulas. Okay, learn it. Okay, of course we will be understanding it later on, but you will learn it. Okay, So I is equals to mr square. For the circulating solid cylinder, it is half mr square. Okay, and remember this thing that where sometimes in the question it's given hollow, and in haste we just apply this formula. Okay, and you will get the answer wrong. Okay, I remember in my time in 2013 JEE mains, there was a question related to hollow cylinder. Okay, and by mistake I applied this, so the question I wrongly marked the answer. Okay, so don't make this mistake. So for the third is the thin rod. Thin rod is simply the thin rod, okay, which has negligible dimension in the this direction. Okay, that is the vertical axis in this. So let's say it's of the length L, and remember this thing. There are two cases. That is one this where the axis of rotation is passing through the centroid, okay, or centroid. Here the axis of rotation is passing through one of its end. Okay, now here the moment of inertia is half ml square, sorry, 1 by 12 ml square, and here it is 1 by 3 ml square. Okay, now you can see that the moment of inertia of this is greater as compared to this, even though they are of same length. Okay, so now you see that the axis of rotation has a key role playing in the moment of inertia calculation. If the axis of rotation is changed, as in this, the moment of inertia also gets changed. Okay, so remember this thing that now that axis of rotation change causes the moment of inertia to change. Okay, now the second thing is that you can see this is lower. Okay, this is 0.25 and this is about 0.33. Okay, so this is lower. Why this is lower? Sorry, not zero point 0.5, it is 100 upon 12, that is something like 6 point something, or 8 point something. Okay, so the point 8 something, so this is lower. Okay, and this is higher, not point 0.8, 0.08. I'm so sorry, I'm little weak in mathematics. Okay, so this is lower quantity. Okay, this is higher. So why this is greater? This is greater because it has more mass distributed at a greater distance from the this axis of rotation. Okay, here you can see that the maximum mass distributed is within this range, that is L by 2 from the axis of rotation. Okay, but here it is L distance. Okay, so you can see this mass in this case it is at L by 2, and here it is L distance. Okay, so that's why this has greater moment of inertia. Okay, the more the mass is distributed outward, that is the at a greater distance from the axis of rotation, the more will be the moment of inertia. Okay, so the fifth is the thin spherical shell. Okay, these proofs are little complicated. Okay, we will be dealing them with them, don't worry. But for now, remember this thing, that is for the thin spherical shell. Again, this is 2 by 3 and this is 2 by 5. Okay, remember this thing that mr square is constant. Okay, because the moment of inertia unit is kg into meter square. Okay, so this will be constant in all the formulas. Okay, so don't make mistakes. Okay, that's the simply dimensional analysis. Okay, for the solid it is again less from this, that is 2 by 5. Okay, why less? Because it is solid. So for the same mass, here the all the mass is distributed at a r distance, and here the all the mass, that is m only, is distributed non uniformly. Okay, so some mass is even less than the capital R. Okay, so that's why the moment of inertia decreases. Okay, now note this axis of rotation, change of axis of rotation changes I, this I have already told you above. Okay, and remember this thing that all above have the uniform density. Okay, it's not like the, let's say in this case the mass is more over here and less over the center. Okay, the mass is homogeneous. Okay, that is there is same composition throughout. Okay, the seventh is the important thing, that is the circular disc. So for the circular disc, the axis of rotation is passing perpendicularly. Okay, remember this thing that here what's the theorem of perpendicular axis comes in. Okay, so this axis of rotation isn't about the, isn't on this plane, it is perpendicular to the plane of the disc. Okay, so this is half mr square. Okay, now did you remember the in the last video we saw that why bicycle tires are made something like this? Okay, it is because we have to give the large moment of inertia for the same mass. Okay, so for the ring, let's say this is a ring. Okay, and what if the tire was a solid disc? Okay, so why it is kept as a ring shape? Okay, so because you can see that for the same mass, the ring has greater moment of inertia, that is mr square, compared to the disc. Okay, that is the half mr square. Okay, the moment of inertia decreases almost by 50%. Okay, so that's why the bicycle tire is of ring shaped. Okay, the more the eye, the more difficult is to start or stop the rotational motion. Okay, So with the large moment of inertia, the tire is able to rotate more so as to reduce the fuel consumption by the engine. Okay, so as to make it the vehicle go more and more. Okay, so that's why the tires are made of this ring shape. So I hope that with this in this video you have understood what is rigid body and what are the good applications of the moment of inertia. Okay, so if you like this video, then thank you and wish you a very good luck. Okay.